All right, so we have already talked about light as a wave, yes?
Yes.
We had some formulas for figuring out wavelength versus frequency, and they are inversely related according to the speed of light. Yes? Speed of light equals the frequency times the wavelength. Yes? Good. So today what we're going to do is we're going to see light as particles. And we're going to see how those light particles relate to electrons and how electrons relate to light. Oh, my computer is being super awesome right now. Super. Okay, so I'm bringing up the camera. So I want to show you this. There we go. I got my camera. All right, so I've been playing with this thing over here, right? And I have these lights that are here and here. There's a little bit of light. You can see these lights came on. So light, when it acts like a particle, can actually do work for us. It's not doing any work yet, though, is it? Anybody hear the water moving? No? How about now? How about now? Please turn the last one on. Okay, so now I've turned on all three lights. How in the world is this light making the water move? What's that?
Magic.
It is certainly not magic. How does light make water move?
Because it's energy.
Light is definitely energy. Can I harness that energy?
Yes.
So, am I making light energy push water molecules around? No.
Not directly.
No. What's the light energy pushing?
Your solar panel.
No, that solar panel is not moving at all. What is the light energy pushing?
Particles.
I couldn't hear you.
Particles.
It's not actually pushing particles. Not in the way we understand particles, anyway.
Electrons.
It's pushing electrons. All right, look at the lights above you. Why do you think those lights work? How do they work?
Run current through them.
I run a current. What's a current?
Electrons.
Movement of electrons. I run electrons through those lights that are above you, and somehow out comes light. I somehow hit this with light, and somehow that moves electrons? How does that work? What in the world is going on there? That's what we're going to figure out today. All right, how does light move electrons, and how do electrons move light? What is that relationship? How does it work? Well, what we're looking at right over here is called the photoelectric effect. So if I shine light into some sort of metal plate, I can knock electrons off of it, make them move through a wire, and generate electricity. That's what electricity is. Electrons moving through a wire. So with the photoelectric effect, I can use light to knock electrons off. Does that make sense? Can I knock electrons off of atoms just by adding some energy?
Yeah.
What are the four states of matter that we talked about in this course? Solid, liquid, gas, and what is plasma?
Gas without any electrons.
Yeah, where'd the electrons go? I knock them off with energy. So if I add enough energy to electrons, I can knock them off. That's what the photoelectric effect harnesses in order to generate electricity. What's interesting is the intensity of the light doesn't matter. The energy within each photon is what matters. we have to understand this in terms of particles. If this were waves, then I could hit the same electron with a wave for 6 seconds, and it would absorb all of that energy, then it would move. But it doesn't work like that. If I hit it with one photon, and that photon doesn't have enough energy to make it move, it doesn't go anywhere. If I hit it with another one, with the same amount of energy, it doesn't get to store up that energy from the previous one. It doesn't work like that. I have to hit it with one photon of the correct amount of energy, at least the right amount of energy, the minimum is what it says up there, in order to make the electron move. Does everybody kind of understand the photoelectric effect? I shine light into metal, it knocks electrons off because I give it enough energy. Those electrons move through a wire, I have electricity, and I can pump water from one of these beakers to another. That's photoelectric effect. Electricity is just the movement of electrons through a wire. It might even be just the movement of electrons, but I'm not entirely sure. Is everybody good with the photoelectric effect? So once we realize this happens, and I don't know the order in which this happened, but in my mind, they understood the photoelectric effect, then they went and said, something doesn't fit. All right, think about where we were in the history of the atom. We had Democritus way back in ancient Greece. Then we came forward and we had Dalton. Dalton stole a bunch of ideas, put them together, made the atomic theory. And then we had Thomson, who showed us what? Oh, wait. The electron. Third time's a charm. And then we had Rutherford, who showed us what? Nucleus. And then we had, who's the last guy? Chadwick, which showed us the neutron. And we said all the stuff, all the mass is in the middle. All the electrons are all the way out on the outside. And in between are vast regions of empty space. Remember that idea, that model of an atom we had, where I had those people walking around that castle that nobody has yet told me where that is in the world, by the way? And we said everything in between was vast regions of empty space. Well, it turns out this isn't true. Along comes Niels Bohr. Niels Bohr actually figures out that these electrons don't all sit on the outside. They exist in levels. And here's the weird part about these levels. This is probably the trippiest thing we'll learn all year. Electrons can exist at level 1. Electrons can exist at level 2. Electrons can move from level 1 to level 2, but electrons can never exist between level 1 and level 2. Think about that for a second. I can exist in my science class. I can exist in my history class, but I can move from one to the other without ever being between the two. How is this possible? Say it again. They teleport. Yeah, weird, right?
I can teleport to my sister.
You cannot, because you are not an electron and you cannot act like a wave.
I don't know.
But they can. And when they act like a wave, maybe they're also acting like a particle, and the particle part of their existence goes through a wormhole. Maybe. I don't know. This is the part about electrons that really tricks me out. Not only can light go back in time, but electrons can teleport. So if it sounds like science fiction, it's not. It's real. And it takes real smart scientists, smarter guys than me, that figure out what all of this means, because I don't get it. Luckily, we don't have to get it. You just have to understand that they exist in these shells. Sometimes these levels are called shells. Sometimes we call them levels. Sometimes we call them orbits, which is problematic. But here's the deal. The closer they are to the nucleus, the lower energy they have. The further they are from the nucleus, the more energy they have. Make sense? Because we said if I hit them with enough energy, I can knock them off there altogether, can't I? And if I can knock them off there altogether, they can go through a wire and I can get electricity. Here's where it gets a little bit weird. Well, you should probably already understand. If closer is lower energy, then further is higher energy. Good. And I already told you this, they can't exist between the levels. So is everybody good with this idea right here, right? Now I said I can use photons, my photoelectric effect that's going on right here. Everybody sees it going on. It's happening at the front of the classroom. I'm using photons, I'm hitting electrons, and they're flying through this wire and pumping water. So if I can use photons to give energy to electrons because they move further away from the nucleus, what do you think happens to an electron as it moves closer to the nucleus? I'll say this again. If I can use photons to move electrons further away from the nucleus, what do you think happens to an electron when it moves closer to the nucleus? No?
There are less of them.
No, not necessarily.
They start shooting photons out.
They start shooting photons out. That's probably the best way to think about it. When electrons fall from way outside, way out here, or even level 2 to level 1, they shoot out photons. And you know what? If those photons have the right amount of energy, they'll be a certain color. That's how we make fireworks.
Is that also how like Bunsen burners their flames are blue?
Yeah, I think so. I'm pretty sure that's how that works. Anybody ever have your Bunsen burner turn a weird color? Like the flame came out like a strange color or something? That would be because there's some sort of extra metal sitting on the edge of your Bunsen burner. And as it gets burned off, I'm making those electrons excited. I'm adding not photons to move them away, but I'm adding fire to move the electrons away from the nucleus. And then as they fall back down to where they're supposed to be, they decrease in energy and shoot out photons. What color photon? Depends where they moved from and where they moved to. And that's what we'll look at here in a second. But first, this guy here, after Niels Bohr figured this out, Max Planck, yes, that said Planck, realized that these objects release electromagnetic radiation in packets. And when they release them in these packets, guess what he called them?
Packets.
He did not call them packets. Sorry, Ant-Man fans. This is what quantum really are, or quanta really are. Quantum doesn't mean really, really small. Quantum means the smallest amount of energy gained or lost by an electron. That's what these packets are. So if you think about a photon, not as a wave, but as a particle, that particle equals one packet of energy. If I can hit the electron with the right amount of energy, my packet has enough energy, then I can move it further away from the nucleus. If I can hit it with enough energy, I can get it really far away from the nucleus and get it to fly away completely and generate electricity. That's how solar panels work. This energy is directly related to the frequency of the wave. Remember we said wavelength and frequency are inversely related? Energy and frequency are directly related. So if I were to draw that, come on. Energy, frequency, directly related. Which means as my frequency goes up, what happens to my energy? It it goes up. As my wavelength goes up, what happens to my energy? It goes down because those are inversely related, right? Okay, and of course, Planck gave us an equation. He said if they go up and there's a relationship between them, this one goes up when this one goes up, there's got to be a constant that I can figure out. That's the relationship between them. And he called it Planck's constant. I don't know if he called it that or somebody else did, but make sure you memorize this. 6.626 times 10 to the minus 34 joules times seconds. Yes, make sure you commit that completely to your memory because there's no way it's on the back of your periodic table. It's definitely not there. It's there. Sarcasm. I know. So what we're going to do 2 practice problems and try to figure out how to use this wonderful formula right here. Actually, I'm just going to do 1 practice problem. Yep, because I got to introduce you to the conceptual stuff that's pretty important that most students never learn. They just learn how to do these math problems. And I think you can learn how to do the math problems on your own. You ready to try one of these Planck math problems? All we're going to do, I'm going to give you one of the 2 variables. You're going to use this equation with the constant and figure out the other one. That's how easy this is. Here's your formula. Energy equals Planck's constant times the frequency. I've even given you Planck's constant on the board. Hey, how much energy in joules does a photon have? It has a frequency of 1.29 times 10 to the 17 hertz. So if I say I'm given frequency, my unknown is energy, my plan is energy equals Planck's constant times the frequency. That's a pretty easy plan, right? I don't even have to do anything because I'm looking for energy, and it's already solved for energy. So no algebraic manipulation required. So then when I solve this thing, I just say energy equals Planck's constant times the frequency. Planck's constant is 6.626 times 10 to the minus 34 joules times seconds divided by, or multiplied by the frequency, right? And my frequency is 1.29 times 10 to the 17. And I'm not going to put hertz. I'm going to put 1 over seconds. That way my seconds will cancel. And now it's just calculator practice. Ready to go, calculator practice. Already?
Yeah.
Nice. You got to put it in scientific notation?
I already had it, so I didn't.
Scientific notation will definitely help you on this one. Because I think we're going to get somewhere near 10 to the minus 17, right? 8.54 times 10 to the 17.
Negative 17.
How many people got 8.54 times 10 to the minus 17? Sweet. I would tell you you're wrong.
5.
Hertz.
Joules. Good. The other way to ask this is to give you the energy and ask you for the frequency. I'm not going to walk through this problem, but that's what this one asks you to do. What I'm going to do now is introduce you to arguably the greatest scientist of all time. If I were to say this person is the greatest scientist of all time, you would say, of course, Albert Einstein. He said that he knew that electromagnetic radiation, that's what ER is, electromagnetic radiation, has wave and particle properties, and each particle has a quantum of energy. It is a given amount. And a photon represents a quantum of energy. And matter absorbs energy only in whole number of photons. So if I need 12 energy and I have photons of 10 and I get hit with one photon and I'm an electron, guess what? I'm not moving. But I can't get hit with 1.2 photons. I got to get hit with 2 photons. I don't know where the rest of that energy goes. So I told you, as electrons move further away from the nucleus, they have higher energy, yes? So if I hit it with 16 photons, I can maybe give it enough energy to fly away. What do I have to know about those photons, though?
Frequency.
Not all photons have the same energy, do they? Because energy is based on frequency. So if I have a certain frequency and I have 16 photons, they might not have enough energy. But if I have a higher frequency, each of those photons will have more energy. The easiest way to conceptualize this is with visible light. We're going to do a little exercise here with that Bohr model that's right in front of you. So we got what, 9 minutes? Yeah, 9 minutes. Two vocabulary words you need to understand. The ground state is where an electron is at, I'll say, it's at the place where it's supposed to be. It's at the lowest energy level where it's supposed to exist. The opposite is an excited state, which means it's above where it's supposed to be. If an electron is excited, it is above its ground state. So everybody understand those two things. Okay, we're going to jump to this. Everybody take out your Bohr electron diagram that's in front of you. And your dry erase marker. If there's something on your board, go ahead and wipe it off. Come up here. Use the marker. Use the marker. Are there any in here? I put out 30 this morning. Maybe 8 or some of
Mine doesn't do these.
Yeah, use the marker. You have a marker? Use the marker. Guys, if you have dry erase marker, you write on the marker that's on your board and then wipe it off. Come grab one. Are there any in there? Do you need my markers?
This doesn't work anymore.
Okay, so here's what I want you to do. If you're in row 1, and I messed this up when I made it this morning. If you're in row 1, you guys are helium. You're helium-4. I would like you to draw, actually, you know what, we're going to go backwards. You guys are nitrogen-14. Okay? So you need to make that nucleus look like nitrogen-14. You guys are carbon-12. You guys are boron-11. You guys are beryllium-9. Lithium-7, and because I like you guys and don't want you to draw a whole lot, you guys are helium-4. Make that nucleus helium-4. When I tell you to make the nucleus helium, what's the first thing you should put in there? What's that? No.
The correct number of protons.
The correct number of protons. You can use a plus or a P for proton. How many protons does it have? Zero.
Right marker over it.
That's a really good question. Do I have the same number of neutrons as I have protons? How do I figure out how many neutrons I'm supposed to put in that nucleus? The mass number, right? So my protons plus neutrons equals my mass number. So if you are nitrogen 14, how many protons should you have? No. How many protons does nitrogen have? Every single time. If it doesn't have 7, it's not nitrogen. In the nucleus.
And then electrons is
On the minimum.
Yep.
In physics, it is what we wanted. It wasn't that you had to get above a minimum, so it had to hit a certain energy level because they can't exist between the rings. You can't.
Yeah, they just go to their energy level, and I don't know where the rest of the energy goes.
If you
Hold on. Hold that thought. Okay, does everybody have their nucleus drawn? Anybody still struggling with their nucleus? Okay, how many electrons should you have?
Same number of protons.
Same as protons. So what you're going to do is in level 1, you can put 2 of your electrons. In level 2, you could put 8 of your electrons. So you see those levels? Draw your electrons. You shouldn't have any in level 3 yet.
Yeah, I know.
Because nobody's above atomic number 10.
Yeah, I know, but didn't you say that they can exist in 1, 2, but not in 3?
They cannot go in between.
But it can go higher.
Yeah, they can go to 3 and 4 and 5 and 6 and 7.
I don't know.
Put 2 electrons around that circle.
How many protons do you have? Look at the thing, how many-
Okay, does everybody have that? Okay, so here's what we're going to do. Here's where it's going to get confusing, so please stay with me. I see a lot of people not looking at me, so you're going to look at me very confused in a second. If you're in this row, your electron in level 2 moved up to level 3. Actually, everybody go like this. Put your hands about right here. Then put them together quickly. That was energy. You just gave energy to your electrons. If you're in this row, right here, your electrons move up to level 3.
All of them?
No, level 2. And then it moved down to level 1. And it shot out a photon of 700 nanometers. That's red. Red photon. How much energy was in that?
I don't know.
Ready, go. If you were here, you're in level 1. Your electron from level 1 moved up to level 3 and fell down to level 2. When it falls down to level 2, it gives off a orange photon. How much energy is in that photon? You're in this row. When you started in level 2, you moved up to level 4 and moved back to level 2. And when that happened, when you came back to level 2, it gave off a yellow photon. How much energy is in that photon? If you're here, you started in level 1, you went up to level 4, came down to level 2. When it went from 4 to 2, you gave off a green photon. You guys, you gave off a cyan photon, and you gave off a blue photon. How much energy is in your photon?
Multiply the frequency.
No, nanometers is length, not an energy.
By the constant, right?
Is this Wednesday?
This two-step, like I think.
They've got to be on the line.
Oh, on the line?
The line is the lever.
Oh, we need to take the wavelength, using the speed of light, convert it to frequency, and then multiply the frequency by length. I did my group.
Whatever you want to call it.
Wait, I get it.
All right, who's figured out how much energy was in your photon? Oh, I see lots of cognitive dissonance out there. What formula did we use for determining the energy of a photon earlier? Planck's constant times the frequency, right? But I didn't give you a frequency, did I?
Gave us wavelength.
I gave you a wavelength. Do you know how to get from wavelength to frequency?
Yeah.
Ready, go. Oh, wait. 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 9 of you wearing jerseys? I think so. And I'm going to pretend you're all sophomores.
Does this count?
Yes, I counted it. Wait, did anybody dress as Jersey Shore and I'm just not realizing it? Because I don't know what that looks like. That's what Jersey Shore looks like.
It's just like, I think it's just looking pretentious.
Oh, I'm good at that.